Okay, so welcome to this new lecture of the course AI and Cryptography. And today, we are going towards the closing of this course, and we're going to cover the privacy issues in machine learning. So in particular, today I will focus, like this morning in particular, I will focus on the part on secure multi-party computation, and then let's see how we arrive, because we need to cover a bit of ground, possibly the part on secure multi-party computation for privacy-preserving machine learning, so how to apply it to the privacy issues in machine learning. I will finish it this afternoon, and then we wrap up quickly by discussing a couple of possible research topics or topics to develop for your assessment. So these are the two main references that you can look at for this part. There is this nice book by Evans, Kolesnikov, and Rozulek called A Pragmatic Introduction to Secure Multiparty Computation, which is quite a thin book, so it's also easy to read, like it's, 100 pages or something, so also for having just a quick reference for the various protocols, and it's available online on the website of the authors. And then this survey about privacy-preserving machine learning that is still a preprint on arXiv, but as far as I saw, it's written quite well, so I advise to look at it just to have a complete overview of what is privacy-preserving machine learning, because of course today we will only see just a couple of possible applications. So in this lecture, like I said, we start with an intro to secure multi-party computation. And what is the idea of secure multi-party computation? Well, the idea is to say, okay, we have a distributed computing setting, and the participants in this setting, in this distributed environment, want to compute a function over their inputs, but they do not want to share their private inputs. So they want to learn the output of the function, of the common function to be computed, without really revealing their private inputs to the others. And so how is it done this? But well, there is like a straightforward solution. If we have like a client-server setting, so we have a single trusted server called a trusted third party, or TTP, and we say, okay, we trust this server to compute the output of the function, so all participants are sending their private inputs to the server. The server will compute the functions that they want, and then it will return the output value of this function to the participants, with the promise of not revealing the inputs to the other participants or to anyone else. Of course, this is kind of problematic because it means that you need to put a lot of trust onto a single entity, so the trusted third party, and that could be a single point of value from an engineering point of view, so it's not the best, not the ideal setup, let's say. And so in many realistic settings, this is not an acceptable solution. So what secure multi-party computation does is to use cryptography, so some of the protocols that we saw in the first lecture and that we will review here quickly. And it uses these cryptographic protocols to, let's say, remove the need of a trusted third party. So basically, the players, the participants in the protocols need to interact with themselves following a particular secure multi-party computation protocol. And by the end of this protocol, they will learn the output of the function that they want to compute over the shared input without learning anything about the input of the other participants. So in general, in secure multi-party computation, we have, let's say, three types of adversarial models that we can consider, and there could be also some kind of combination in between the three. So we have the usual setting that is the semi-honest adversary. So basically, we assume that the participants in the protocol are semi-honest in the sense that they abide by the rules of the protocol, so they follow what is prescribed by the protocol for secure multi-party computation. But they are also curious, so whatever they can learn by following the rules of this protocol, they will try to discover it. But there is no malicious intent. On the other hand, there could also be malicious adversaries, malicious players who tries to actively, let's say, find what is the private input of the other participants, and also by deviating from the protocol. So in this case, we talk about a malicious adversary. And finally, we can have two or more colluding adversaries. So they collude, they make an alliance in order to see, let's see if by combining our information, we can learn something about the values of the private inputs. If you remember what we saw a couple of lectures ago about secret sharing, which we will also see in this this day within these two lectures, colluding adversaries is something similar addressed by secret sharing. As a matter of fact, we said that all colluding sets of at most k-1 adversaries or players cannot recover any information about the value of the protocol. So in order to, let's say, explain this thing of how to compute the, let's say, a function over two inputs that needs to stay private, let's play like a game using these cards. And for this, I first need to change the slides quickly. So let me see here. Okay, well, yeah, okay. So we start with this metaphor of explaining secure multi-party computation using set of 5 cards, playing cards. So we are doing crypto without computers in a certain sense. So the idea is that we have Alice and Bob who want to find out if they have an interest in common. For example, they are going out on a date and they want to see if they like each other in order to determine whether to see each other for a second date or something like that. So the classic protocol would be that Alice, for example, reveals one of her interests to Bob, such as, I love rock music, what about you? And he says, in the ideal case, yes, me too, like I also love rock music. So in this case, there is a match, and okay, they like each other and they can continue to see each other. This is the ideal situation, however. What happens if someone, like one of the two, has a kind of a particular interest that the other doesn't have? Like Bob, for example, could say, I have a very obscure interest, like I love reading dictionaries, what about you? And well, understandably, she could say, no, I don't. I mean, it's quite boring. So, okay, in this case, Bob will be kind of embarrassed because he showed an interest that the other party doesn't have. So this causes some kind of embarrassment. So what the problem is that if we have an interest that is unrequited, so only one of the two persons has it and the other doesn't have it. So this is embarrassing for the part who reveals to have this interest, right? So the question is whether it is possible to find a protocol such that Alice and Bob reveal their interest, but only if both of them have this interest. So in the ideal case. In all the other cases, so the other 3 combinations, neither of them have an interest, or only one of them has an interest. Then in those cases, the other party cannot understand what is the interest or the presence or absence of the interest in the other party. Okay, so how do we do this? First, let's see what we want to achieve. So what is our goal? So we want to find a protocol where if Alice and Bob have both an interest, then they can reveal it, and that's clear. If one of them doesn't have an interest, then he or she, Alice or Bob, can't understand whether the other person has this interest or not. And now the question is, can it be done? Yes, we can do it by using a few playing cards, like 5 playing cards that I have here. So now I will need a volunteer to come and then... Okay, so basically the idea is the following one. We have these 5 cards. So we have, let's say, 2 red cards, 2 ace of hearts, and then we have 3 ace of, these are spades, I think they are called.
Flower.
Yeah, they are flowers, but I think that in English they're called like spades or something like that. Clubs, right. Yeah, spades are the other ones, what we call picche in Italian. So it is that one of the 2 players gets 1 red card and 1 black card. So you're taking this. And I do the same, so I will have, as a second player, I will have the red card and the black card. And then we have one final black card, which is put face down on the table, okay? Now at this point, we need to think of an interest, let's say, that we want to find out if we have it, like something very, I don't know. Let's say, just for the sake of example, so we know how it works, we know already that it will be, let's say, a positive answer, so we both have an interest. Let's say, do you like pizza? I guess that everyone like pizza, so okay, it's not secret, but anyway. Basically, the idea is that he starts by saying, okay, if I like pizza, then without showing to the other player what is happening, I will put my red card behind the black card, okay? So in this way. Okay. And if it doesn't, then he will do the other way around. So we'll put the red card on top, on the foreground, so behind the black. Behind there will be the black card. Okay, so when you have done this particular choice, you can put the your card face down on the remaining black card, so on top of that card. Yeah. And on the other hand, the second player, so me, I will do the other way around. So if I like pizza, then I will put the black card behind the red card. Another way I will do, otherwise I will do the other way around. So okay, I did my choice, and then I put my two cards also on the top of the other three. And then in turns we start to do some random cutting. So you can continue to do a random cut, just a cut, so just to raise the two, yeah, like this. And then we continue in turn until we are satisfied that there has been enough shuffling, yeah, let's call it like that, enough randomization. So, okay, are you satisfied? Do you want still to?
Just do another one.
Okay.
We are on our way.
Okay, good. Then at this point, we are going to reveal the 5 cards in circle. So we'll have this, this, and this. And then from this disposition, you can see it here from the from this circle that we have the 2 red cards that are close together. And this means that we both have this interest. So we both have we both like pizza in our example. Why is this the case? So the idea is that if one of us or neither of us didn't like pizza, then we would have came up with a situation like this, for example. So we would have a black card that is at least one black card that is separating the 2 red cards. And what is the reason? Well, the reason is that once we did our initial arrangement of the cards, we had the first black card that was put here, and this acts as a kind of a separator. Then he was the first to express his commitment, let's say, so his liking or not of pizza, and he would put like the red card, since he liked pizza, behind the black card, and then he would put this face down. Me, instead, I did the contrary, so I put like the red card on top of the black card, and then at this point you can see that if we arrange the deck in this way, the 2 red cards are already close to one another, because we did the complementary operation. And then if we just do cuttings as a shuffling operation, then their neighborhood is not changed, because they are just a cyclic rotation. So if they are close together at the beginning, they will stay close together at the end, like in this case. If they are not, they will stay separated for as many rotations you want to do. The fact is that if we are in the case where, for example, we are here, so the output of this matching protocol is 0, so not both of us like pizza, then the guy who doesn't like pizza cannot understand whether the other likes pizza or not. Why? Because basically the situations from where the other one is liking pizza or not is indistinguishable from the point of view of this circle of cards from the case where neither of us like pizza. So this is the idea of computing what? Of computing a secure AND function between the two, because we are trying to do matching. Okay, so at this point, I think that we can go back. So enough of playing games in a certain sense, and we can go back to the slides. So I can remove this and go back to where was it? It was here. Yes. So let's put it here again. So okay, this is nice, the thing of using cards, and it's a nice metaphor because it tells you, for example, when one of the two players is choosing how to arrange his or her cards, then he or she is doing what is called in cryptography a commitment. So he or she is committing to a private value, and then he or she cannot change it later during the protocol. And why is that the case? Well, in this case with the cards, it's because once we have arranged them, we are putting them face down and then we are shuffling them. So we are not able to recognize them anymore where they end up, because they are, of course, the cards needs to be indistinguishable both from the, let's say, the back, and on the front, they can only be distinguished by their color. So either red or black. Now the problem is how to do this. So we kind of solved how to compute AND using a two-party computation, secure computation protocol. Now the idea is how to do these commitments, how to do these protocols using cryptography, because we are not using cards, of course, to encrypt our messages. We are saying, okay, our private inputs are secret bits, basically. So in order to do this, we need to introduce the idea of Oblivious Transfer that was, let's say, invented in like around the 80s, in 1981 in particular. It was invented by Michael Rabin, and then it was later refined by even Goldreich and Lempel in 1985, a few years later. And the idea, so here in particular, I'm showing you this version of the protocol, the one from 1985, because in Rabin it's a little bit different, let's say. So in this case, using this refined version, I can show you how to compute the secure AND, for example. So it is that Alice, this seems something unrelated. We will see later how it is how it connects to the secure AND computation. So in this case, Alice wants to send a message, so a secret bit, for example, to Bob, but she does not know what she is sending. And this is kind of a contradictory thing, it seems. And like always in cryptography, we are facing problems and situations that seem impossible to accomplish. But we see now how to do it using RSA. So first, we need to review a bit RSA. Because we showed it only in the first lecture, so just to be sure that we are on the same page. In this case, I will need a bit the blackboard. If you remember, RSA is a public key cryptography algorithm, and the idea is quite simple. We want to be able to find a way where Alice can send a message to Bob, encrypted, using the public key of Bob. And then Bob has his own private key, and in this way he can decrypt the message. So in order to do this, we first have a setup phase for our protocol, and we call this the key generation of RSA. Okay, so the first thing that needs to be done is that, let's say, Bob, for example, is or let's say Alice, because this will be better for our setting. No, actually, we need still Bob, because this is consistent with this slide, but no problem. So we say Bob will choose, let's say, two large primes, P and Q. What do we mean by large? For example, encoded by a string of 2048 bits. Okay. And after this, he computes the RSA module, which is simply the multiplication of P and Q. Okay. And we know that this is a one-way function, at least it is considered to be a one-way function using classical computer and not quantum computers, if they will ever become available in the power that is needed to solve the factorization problem. After this, he computes also the totient function of Euler, so phi of n, which will be, in this case, because we are dealing with prime numbers, p minus 1 times q minus 1. Okay. So then he selects a random decryption exponent, so d, which is such that d is included between 1 and phi of n. Okay. And such that d is also coprime with phi of n. So it means that the greatest common divisor between d and phi of n is equal to 1. Okay, now he will do what? Well, basically, this fact means that since it is coprime to phi of n, it means that d has a multiplicative inverse over the multiplicative group z of phi of n star. So it means that we can find E, which is in that same multiplicative group, so z of phi of n star, such that if we multiply E and D, then the result will be congruent to 1 modulo n. What does it mean? It means basically that if we multiply this, we are getting the unity of the group, and this is good because we want to make sure to be able to decrypt. So if we first encrypt by exponentiating with E, and then we decrypt again by exponentiating by D, then we are going back to the original message. Okay, now the public key for Bob will be public the pair RSA module n and the encryption exponent E. The private key that he keeps for himself will be the private decryption exponent D. And moreover, there are also other parameters that Bob is not revealing. They are not part of the decryption key, let's say, but P, Q, and also phi of n need to stay secret. Otherwise, a potential adversary like Eve could break the crypto system by factorizing the RSA module. Now, so this is the key generation phase of the algorithm. Everything clear, like you remember how it worked, more or less? So now we go back to the slide and we show how it works. So how Alice can send an encrypted message to Bob. And the idea now is quite simple, because once we have done this preliminary setup phase of key generation, then Bob will send the public key, so the module N and the encryption exponent E, to Alice. Alice will choose a message to encrypt, which is X here on this slide. And it is again a number between 0 and n minus 1. So it is a message in the multiplicative group. Well, no, actually not the multiplicative group. It will be the whole the whole residue ring Zn. And then she computes this exponentiation, so x to the power of the encryption exponent modulo so it does the modular reduction of the RSA module n. And then on the other hand of the channel, Bob will decrypt the message x by computing y to the power of d modulo n. So we said that e and d are one the multiplicative inverses of another, and thus this, if we exponentiate x to the e and then again to the d, we will go back to x, basically. There is a bit more of algebra involved here, but they are just details, so we are not going to look into them. The bottom line is that if she tries to intercept anything in between here, basically needs to factorize n in order to break the crypto system, so to recover the message without knowing the decryption exponent, or to recover the decryption exponent. Now, how is it related to secure multiparty computation? Well, in secure multiparty computation, we saw that we were interested in a very specific setting up to now, that is like the computation of an AND gate, let's say, in a secure way. So we want to compute the AND between two secret bits that are held by two separate parties. And here what we need is to use RSA to do this Oblivious Transfer protocol that we introduced a few slides before. And in order to do this Oblivious Transfer, we first need to introduce also the concept of hardcore predicates. So what is a hardcore predicate? Well, basically, besides the formal definition that you have here on the slide, intuitively the idea is that if you have like a function, let's say f, example of one-way function or something like that, and then the output of this function is encoded in bits, let's say, then you can compute, let's say, a predicate, so a Boolean formula out of the output of this function, or sorry, not of the output of the function, but on the input of the function, so x. And then the idea is that an adversary is not able to predict what will be the value of this predicate, so the value of this Boolean function HC, this hardcore predicate, with a probability that is significantly larger than 1/2. So it means that the probability that any PPT algorithm, probabilistic polynomial time algorithm A, is able to predict the correct value of the hardcore predicate will be smaller than or equal to 1/2 plus a negligible function of n, where n is the size of our input, where the input actually is sampled with uniform probability. Okay, so it is very difficult to predict what will be the next value of this bit of this hardcore predicate. And as a matter of fact, you can also use this from a theoretical point of view to construct pseudo-random generators, but we are not going to look at this now. The idea is that we want to use hardcore predicates to, let's say, be in a specific setting where we use RSA to encode a single bit. What is the problem if we try to do this, like to encrypt a single bit using RSA? Well, the problem is that the modular exponentiation won't work in this case, because if we do a straightforward encoding from the bit 0 to the value 0 inside the residue class ring Zn, and the same with 1, if we do 0 to the power of e will be 0, and 1 to the power of e will be 1 for every possible values of the encryption exponent. This is just simple algebra. So the problem is that we cannot encode a single bit in this way using RSA. So it can be proved that the least significant bit of the plaintext of RSA is a hardcore predicate for the modular exponentiation operation, so x to the power of e modulo n. So if we encode our plaintext x in the residue class ring Zn, then the least significant bit of this bit string is a hardcore predicate in the sense that we introduced, that we defined in the previous slide. So what is the idea now is to, let's say, come up with this randomized version of RSA where we are encoding a single plaintext bit, so the secret that we want to send, single secret bit that we want to share for secure multiparty computation, using the least significant bit of the input of RSA. So the idea is that we put the least significant bit to the secret that we want to set, either 0 or 1, and then the rest will be random garbage, basically, in the string that is encoding the input. Now, how does it work? Well, assume that Alice wants to send this secret bit 0 or 1 to Bob, then she does the following protocol. So she takes again the public key of Bob, as before, and then she generates an integer at random, so with uniform probability, such that this integer is smaller than the RSA module chosen by Bob divided by 2. So what does it mean? It means that if we multiply x by 2, this will be smaller than the RSA module of Bob. And at this point, she will send this ciphertext to Bob. So it will be twice x plus the initial secret bit b, exponentiated or raised to the power of the encryption exponent of Bob. Modulo is RSA module. What does it mean? Well, it means that here, since we are computing, let's say we are doubling this random value x, then we know that its binary encoding will have a 0 in its least significant bit. So if we sum a bit here in the least significant position, this will actually hold the secret bit. So this could only happen that it is not working if this part here is odd. So if it is odd, then it is changing, like it is flipping the value in a certain sense. Instead, here we are sure that the least significant bit will be exactly the secret bit chosen by Alice. And then at this point, it is quite simple because Bob will just compute the decryption that will be 2 times x plus b. And then it will take the least significant bit, and this will be the secret bit that Alice wanted to send. Okay, why did we do all this machinery? Well, okay, this is just some other remarks about randomized RSA. And okay, basically the fact is that cryptanalysis become very difficult if you want to encode like an entire message. So not just a single bit, but let's say each bit of a larger message by using this trick here. So it becomes very secure, but it's also very inefficient. But that's okay because for our purposes, we are interested only in using sending a secret bit, so not an entire message. Now, how does it work with the protocol of Oblivious Transfer that we introduced before? So the idea is that, well, unfortunately now I cannot draw on the blackboard, but I will try anyway. This was just to keep a reference, let's say, for how it works, so I can still follow it from my notes, let's say. Because except of beside, let's say, looking at the particular steps in order, it is also useful to it is also useful to visualize it over a space-time diagram. So, assume that Alice wants to send, well, doesn't want to send at the moment, but she has Alice and Bob, so we put them here. Okay. So here I will put, let's say, this slide here simplified. So Alice has 2 secret bits, M0, M1 in 0, 1, okay? And then she generates a key for RSA. So a triplet, let's say N, E, D, and then she sends the public key to Bob. So N and E. So here it's still the same, basically. It didn't change a lot. Then she will also send 2 random bits to Bob. so x0 and x1 in 0, 1, which are random. Let's say that we use this particular notation for saying that they are random. So we put like this arrow to the left, and then we put the dollar symbol over it. This is standard notation in some crypto papers. Okay, so now she has sent this information to Bob. Bob, on the other hand, will do the following things. So he will choose here a bit B, either 0 or 1. So this bit basically indexes the secret message that he wants to learn from Alice, either M0 or M1. So basically what you want to know is MP. And he chooses this in a particular way. We will see after this how to solve the secure end computation exactly in this way. Okay, now he also generates, so he will have his B here, and he also generates a random K, which is an element of Zn. Now what he sent back to Alice is the following operation. So he computes V, which is equal to xb plus k to the power of e modulo n. This is also called the blinding in cryptography. Why? Well, basically because what he is doing, Bob, is to first encode or encrypt K, so the random message that he chose here to send to Alice, using the encryption exponent of Alice. Okay, and then he also adds what? He adds either x0 or x1, chosen with the bit that he wants to learn from Alice. So xb, so either x0 or x1. So basically it is called blinding because Alice now doesn't know what he chose for B, right? And he cannot understand it like directly because he has encrypted this with this particular formula. So on the other side, what Alice will do, let me put like an asterisk here and let's go back here. So Alice, this would be the asterisk. So she computes these two quantities. So K0, which is V minus X0 to the power of D mod N, and K1, which is V minus X1 to the D mod N. Okay. So if you look at these particular formulas here, you notice that we are basically deblinding the value V, but Alice doesn't still know whether it is K, whether basically Bob chose 0 or 1 for B, because it could be both of these. Let's say the original K that was chosen here at this point. So in this sense, now you will see why it is called oblivious, because once she has computed this, then she will send back to Bob the following two messages. So we will have M0 prime, which is M0 plus K0, and M1 prime, which is M1 plus K1. Okay. And finally, what Bob does, say here, is to compute this message. So MB, which is what he wanted to achieve, which will be equal to MB prime, so one of these two, and still Alice doesn't know what is B. So MB prime minus K, and he knows K. So we are done now, because basically Bob has retrieved the secret bit now, MB, by deblinding, let's say, the initial random value that he chose, K, from the blinded message. And on the other hand, he cannot learn what is the other message, the other bit, because in order to compute the other bit, this would be MB XOR 1, so the complement, the one complement of the bit B that he chose. And the fact is that in order to compute this, he needs what? He needs to know D, the decryption exponent as well. But he doesn't know the decryption exponent because it's the private key of Alice. So basically, he can only learn MB, that was the original message that he wanted to learn. So basically, this tells you that Alice is like doing an oblivious transfer in the sense that she's sending both messages, both secret bits, but they are encrypted in such a way that Bob can only decrypt one of them. So this is the idea of oblivious transfer. And it can be, of course, generalized to, let's say, this is called also 1 out of 2 oblivious transfer. You can have in general 1 out of n oblivious transfer protocols and then k out of n oblivious transfer. We are not going again to look into all the details. And here on the slide, you can see the, let's say, the description, the textual description of this protocol. Now, we said, okay, we introduced like a lot of machinery, like we reviewed RSA, we said what is an arc or predicate for RSA, we understood how to use this to encrypt a single bit with randomized RSA, and then we used this to solve the oblivious transfer problem. Now, how do we apply this to compute the secure end? So what we started in the beginning using the card. So the idea is that here Alice will have 2 bits, the M0 and M1 that we saw in the protocol, and one of these will be 0, always 0. The other one will be X, so her private input, whether she likes pizza or not, for example. 0 she doesn't like, 1 she likes pizza. Bob, on the other hand, has B, so the private input, okay? And this B will be what? Will be basically what selects either 0 or X, the secret messages of Alice. Now they execute the 1 out of 2 oblivious transfer protocol that we just saw. For example, using RSA, you can use a lot of other public key encryption system, like for example, the Gamma crypto system, but RSA is sufficient. And in the end, after this execution of the 1 out of 2 oblivious transfer, then Bob will get 0 when the secret bit of Bob, B, is 0. And 1 when the secret bit of Bob is 1. So actually this is implementing the secure end, like we said in the beginning, like with the initial properties that we saw in the slides with the card, right? Because if he doesn't like pizza, for example, then this will be B is equal to 0, and this B is equal to 0 is equivalent to this message here that is always set to 0. On the other hand, when he say, okay, I want to see what is, well, he doesn't know, but he's saying, I like pizza, so I want to see also what is the other bit. In this case, he will get 1 only if he's selecting the second message here, that is the private input of Alice, but he cannot know this because this 1 here will just be the result of the secure end. So it won't reveal, it will reveal actually that it is 1, since it is also 1 here for x, basically. So this is the idea, in a certain sense, of using Oblivious Transfer for the secure end protocol. Let's see what time it is. Yeah, okay, we still have a bit of time. Now, we move to the next topic, which are garbled circuits, and we will see also how to compute the secure end using garbled circuits, which they are also based on Oblivious Transfer. So the idea here is that, okay, so this is a protocol that was introduced by Yao in 1986. Here you can see the reference. And the problem is always the same. So we have a function, so for example, the end function, and we have two private inputs, x and y. We want to compute this output of this function without revealing the private input x and y. So the idea is to convert the function into a Boolean circuit, so something like this, for example. And then we garble this circuit in a certain way so that we can implement this secure multi-party computation of this Boolean circuit, of this function. So we start with something simple, that is the computation of the end function. So let's see it here. Yeah. Let me see if this slide, yeah, no, this is for general garbled circuit. So let's go back to the blackboard. Okay, where is the eraser? Do you have any questions up to now? Well, everything is fine. Okay. So, garbled circuits. Okay, so we have our circuit, which is quite simple. So we have Alice that will give a private input x, and Bob, who will give a private input y, and we compute this circuit. And this will be z, that is x and y. So the truth table is quite simple, because we have here, let's do it like this, x, y, and z equal to x and y. So all possible 4 combinations are 0, 0, 0, 1, 1, 0, and 1, 1. And the output will be 0, 0, 0, 1. All right? So this is the table of the function that we want to compute, and this is the equivalent circuit. So the idea now is that first Alice, in the protocol, she will chooses symmetric keys. So, for example, using keys for the AES encryption algorithm. So here we are in the symmetric setting. And then she chooses these symmetric keys in this way, so randomly. And 2 for each wire. So in this case, we have in total 6 random keys, okay? So each wire here, so this, and this will have 2 keys associated, random keys. And the idea is that they are associated to either 0 or 1, each of these two keys for each wire. So we can rewrite the table here in this way. This have x, y, and z. So we will have x0, y0, x1, y1, let's do it like this, x0, y1, x1, y0, and x1, y1. Okay, so these are the keys for the input values. X0 is the encryption, or let's say the random key for 0, and y1 is the random key for, x0 is the 0 for the x input here, so for this wire. x1 is the value, the encryption of the value 1 for this wire here, and the same thing for y0 and y1 for this wire here. And finally we have, well, z0, z0, z1, z0 and z1. So here we put the encryptions of zeros and 1 in the output. So there will be this, that is the encryption key for 0 in the output, and this, only this row here, that is the encryption key for the value 1 in the output. So we are reflecting the same truth table here, just we are changing the labels. Instead of having zeros and 1s, we have the corresponding secret keys. Okay. Now what Alice does is to compute the encrypted version of this output table here. So she will apply, for example, AES. Let's do it like this, maybe. So here we will have AES of Z. So we will do the encryption of what? Of the two keys x0 and y0. So x0, y0 of z0. What does it mean? It means that we are using these two secret keys for x0 and y0. So for the encryption of the value 0 on the first wire and the encryption of 0 on the second wire, to encrypt the key in the output when the output is 0, z0. What does it mean that here we are using two keys? So we are doing twice the encryption. So first with one key, and then the result so we are encrypting this key twice, basically. And then we do the same for the other keys. So E of x0, y1 of z0, E of x1, y0 of z0, and finally E of x1, y1 of z1. Okay, and this is all good. The next step would be to garble this circuit. What does it mean to garble? It means to compute a random permutation of the output column of this table. So for example, we will end up with this part here. So let's say, let's put it like here, for example. So this was step 1. Step 2 was to generate the random keys, which we already did here. So yeah, okay, this was step 1 actually. Step 2 is to encrypt the values of Z, so Zi, and then becomes the garbling, which means to randomly permute the column of Z. So for example, we will end up with this particular, let's call it G for saying garbled AES of Z. So for example, we will have E of X0 Y1 Z0, E of X1 Y1 of Z1, and E of X0 Y0 of Z0, and finally E of X1 Y0 of Z0. So we moved these here, and then we moved 0, 1 here, and then we moved 1, 0 here, and finally 1, 1, we moved it here. So this is the garbling, let's say, this permutation here. Now, what Alice does is to send this permuted table, so this last column here, to Bob, and the encrypted label of her input. So maybe let's erase here on the left. It's a very small blackboard, actually. Okay, so here we are at step 4 now. So Alice sends what? Sends the permuted table, so what we call G of AES of Z, and also the label, so the encrypted version of her private input. What does it mean? It means that if she has 0, for example, she will encode this X0, so she will send the symmetric key X0 basically to Bob. Otherwise, she will send X1. So she will send XA, where A is either 0 or 1. Right? And finally, Bob retrieves his own input. So Bob does like, he does that, so he retrieves the encryption of, let's say, where is it? Here, Y of B. But how can it do that? Because YB is basically, so B will be either 0 or 1. And like we said, these A and B will be the secret bits of Alice and Bob to compute the secure end. So now he says, okay, I want to see what is the encryption of YB, so the symmetric key corresponding to YB, so either Y0 or Y1. But how can it do that since it only knows like this and the permuted table? Well, he can apply Oblivious Transfer. So he will use 1 out of 2 Oblivious Transfer to retrieve this. And this is easy to do because we saw before using Oblivious Transfer how Alice can send both YA and Y0 and Y1, so the 2 encryption keys for Bob, either if he chose like either 0 or 1 for this secure multi-party computation of the end function. And she doesn't know what she is sending in the end because of Oblivious Transfer. So Bob will learn exactly Y of B, the random key to encrypt his own value. And at this point, he decrypts G of AES of Z. What does it mean? It means that he has this column at his disposal, and he knows X A and Y B. So he will do the decryption of this encryption here using these two keys for all possible rows. What does it mean? It means that in the end, only one row will correctly decrypt to either 0 or 1, because all other stuff with overwhelming probability will just decrypt to random garbage, right? Well, actually not with overwhelming probability, with probability 1, because the encryption of AES is also deterministic in this case. So only one of these row will either say 0 or 1. And at this point, the protocol is done. So he learned what is the output of the end function without understanding what is the value of Alice, because this would be, let's say, a random AES key, and it doesn't know whether it is encoding 0 or 1. And then the last part, well, I didn't write it here, but the idea is that then Bob sent back the decryption of these to Alice, because it will be, once he finds the correct row, he will send back that value back to Alice. And again, also Alice cannot know what is the value of that Bob chose because of Oblivious Transfer. Okay, so yeah, let's go back to everything clear. Like, this is maybe a bit more complicated than the usual things, but okay. So in general, we said, okay, now we know how to compute the end of two secret bits using secure garbled circuit construction that is relying upon the Oblivious Transfer protocol from Rabin. So, well, not from Rabin exactly, but from Evans and the other from 1985. Now, what is the situation if we want to compute like a garbled circuit of a generic function? So we will have a generic Boolean circuit in the end. And the idea is, we are not going to do exercises in detail because we don't have the time, but the idea is that Alice is garbling the table of each gate that is composing the circuit. So she will apply the garbled circuit construction here, 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 and here. So for each wire, she will get like two random symmetric keys for AES for 0 and 1. And then she will do the garbled circuit protocol for each of these gates, and each of these gates will be giving an output that will be used as an encrypted version for the next input in the next layer. So the nice thing about this construction is that Oblivious Transfer, we are not going to delve into the details of this because it would require a bit of development more of this topic. But the nice thing is that Oblivious Transfer is only needed in the first layer of this circuit. So we only need it basically here, compute the garbled circuits of this first layer, let's say, of the Boolean function. For the rest, on the other hand, you only need a symmetric encryption algorithm such as AES, for example. So in that case, it is quite efficient. Although, let's say that also today, like garbled circuit, like it's still used more from a pedagogical point of view, because of introducing like the idea of secure multiparty computation. Actually, what it happens is that you use, most of the time you use a secret sharing. And for secret sharing, actually, I think that, yes, so this was the last slide. Yeah, I think that actually for the moment we can stop here, and then we will pick up later from here with secret sharing, and then finally we conclude with a quick application of how to employ this for privacy preserving machine learning. Any questions so far? So here this morning we saw, let's say, the cryptographic part of this topic. So secure multi-party computation for general circuit, but you can already understand or perceive, in a sense, how you can use this for secure evaluation or private evaluation of neural networks, because basically here what you have is a circuit, and this circuit is a graph that is then implementing a neural network. There are some technicalities, of course, because here we are considering Boolean circuits. So for example, if you have Boolean neural networks, then it's easier. Otherwise, you need to do something more, like, for example, if you have a multiplication or a scalar product, for example, then you need to say, okay, I'm using these to compute the multiplication of only 2 bits, because the end would be the multiplication. And then XOR would be a sum without a carry, but then you can modify it in order to have also a carry and then have like a normal sum. And then from there you combine this in a more complicated Garbled circuit in order to get the operations that you need for an inference in machine learning. Okay, good. Then yeah, see you later.